So we are going to see another problem. Let's write the problem here. So this is problem number 7. So if you didn't watch the problems till 6, please go to my previous videos and watch. So here the question is given: a stepped bar is subjected to an axial applied load. Axial applied compressive load. How much? 35 kilonewton, right? Find the maximum and minimum stress produced right? So the question is given: a stepped bar is subjected to an axial applied compressive load, that is 35 kilonewton, right? So he is asking to find maximum and minimum stress produced. So let me draw here. So it is a circular section. And the figure will be given in the question. So the axial load, compressive load, so because it is fixed, it is grounded, so it will apply the force from the bottom, right? So obviously it will become a compressive load. So that is 35 kilonewton, right? So now in the question it is given that this bar is having 2 centimeters of dia and this will be 3 centimeters, right? So this is the question. We'll try to write the given data. So given data. So axial load is given, that load P is given, that is 35 kilonewton, right? So kilonewton will convert into newtons. 35 into 10 to the power of 3 newtons, right? So dia of upper part, so take this as upper part and lower part. So upper part will denote by D1 will be 2 centimeters. If I convert into mm, it will be 20 mm, right? So dia of lower part D2, that is 3 centimeters. If I convert into mm, it will be 30 mm, right? So now we'll find out the area of the upper part, that is upper bar, and then we'll find out the area of lower bar. Okay, the load is given, so we'll write area of upper part A1. So we'll take A1 for area for upper part, so that is upper bar, which is subjected to compressive load. So we'll find out the area first, that is, it is a circular section, right? So if you see the top view, it will be somewhat like this. Right? Diameter of this is given, that is 2 centimeters, and diameter of the lower part, that is 3 centimeters. Right? So it is a circular section that will be, the area will be pi by 4 d square, the pi by 4 d1 square. We know that is a1 pi by 4 into 20 square. So that is how much? It will be 3.4.159 mm square. Right? So now let us find out the area of lower section, that is pi by 4 into d square, that is pi by 4. What is d here? 30 mm. So 30 mm square, that will give us to put this value in the calci. Same with the answer, that is 906.85. If I am wrong, please correct me. Right? So now we will find out the area of the upper section and the lower section. Next we'll find out the maximum and minimum stress. Right? So what is the maximum stress and minimum stress? So load is applying on the top part of this bar. That means this portion will undergo the maximum compression than the lower part. Right? So when you apply a force on a material, so the upper portion, the upper part will have a maximum stress than the lower part. Right? Yeah. So let me erase this. So the maximum stress, that is load upon area. So load upon area, that is A1. So what is the A1? And we know the load, that will be 35, that is axial load given, 35 into 10 to the power of 3 upon area 1314.159. We will get 111.408 Newton per mm square. Right? So this is the maximum stress of area 1. So now we'll find out the minimum stress. Minimum stress equals to load upon area, that is A2. We know the load is common, 35 into 10 to the power of 3 upon 706.85. Right? And the answer will be 49.515 Newton per mm square. Right? So this is a minimum stress which is applied on area 2. Right? The stress will be equal to the load divided by the area. The stress will be equal by the load divided by area. Hence the stress will be maximum where area is minimum. Right? So this area is minimum. We know that this area will be minimum, so that wherever the minimum stress, so minimum cross sectional area, that means there will be maximum load, maximum stress will generate, right? Now we'll see a analysis of bar of various sections. Analysis of bar at various sections. This is a new topic. Right. So we'll try to analyze a bar of various section. Bars of various or varying section, varying in cross section, right? So how a bar will have a variation, right? So let me draw here. Let's say this is the front part, then there will be sudden increase in cross sectional area. Right? Let's say this is the area 1, area 2 and area 3. When I apply a tensile load P, so what will be the stress variation? So in various cross sectional areas. So let's say this is section 1, section 2 and section 3, right? With the length of, let's say L1, let's say L2. For area 2 the length will be L2, and L3 for area 3 and section 3, right? So now we'll see each section is same axial, having a same axial tensile load, that is P applying a tensile load. So each section will have undergo a tensile load, yet the stress and strain are changed, right? Why? Because of this cross section, because of the change in length will be different, because when you apply the same tensile load for different cross sections, there will be some change in stress and strain, right? The total change in the length, will be obtained by adding the changes in the length of individual section. So if you add individually, then you will get the actual stress and strain. So here you can write each section is same axial load, right? That is P. Yet the stress, strain and change in length is different, right? Will be different. Now the total change, so how you find out the stress and strain? The total change in length will be obtained by adding the total change in length will be obtained by adding the change in length individually. Changes in length individually, right? So this is how we can analyze. So you have to consider each section 1 at a time, section 2 at a time, and section 3 at one time. Then we can add on all together to find out the change in length, right? So once again I will repeat here, P is a load, axial load, and L1, L2, L3 are the length, and A1, A2, A3 are the areas. So E will be the Young's modulus, right? So here A1 and L1 will be the length and cross section. So first we'll try to find out the stress in section 1, then again stress in section 2, stress produced or obtained in section 3. Okay. L3, L2, L1. Yeah. Stress for section 1. Right? That is sigma 1. Let us consider sigma 1 for stress obtained or produced in this area 1 or section 1. So sigma 1 will be load upon area of section 1. So we are analyzing this individually, then we are going to add upon. So that is area of section 1. So let's say P by A1 will be the stress for section 1. Similarly, stress for the section 2, that will be sigma 2 load on area of section 2, right? So that will be sigma upon A2. Similarly, for section 3, the stress will be sigma 3, that will be P upon A3. So this will be the stress for section 3, right? So now we'll try to write strain. The strain obtained, strain in different section are obtained, strain in different section are obtained. So we are using stress Young's modulus to find out the stress. The strain of section using Young's modulus, are also known as modulus of elasticity, right? That will be E equals to stress upon strain, that is sigma upon epsilon, right? From this we can find out strain. So here from this equation, so we'll write epsilon equals to sigma upon Young's modulus, right? So now I can write, so this is for section 1. So you can write sigma 1 here and epsilon 1, right? And we know that stress is nothing but load by area, that is P upon A1, right? A1 multiplied by Young's modulus, right? So similarly, the stress for second section will be the strain for section 2. So that is epsilon 2 equals to sigma 2 upon E. So we know that sigma is nothing but stress area, load upon area, that is epsilon 2 equals to P upon A2 E. This will be for section 2. The strain for section 3. The strain for section 3, what it will be? The epsilon 3 equals to sigma 3 upon Young's modulus. So from this, epsilon 3 equals to, that is load upon A3 E. This will be for section 3, right? For section 3. Is it clear? Right? So now actually we know that the strain is nothing but change in length by original length. So now I can write the strain in section 1, that is change in length of section 1 upon original length of section 1. So that is actual length of section 1, right? Clear? So epsilon 1 equals to, let's say dl1 will be the change in length by original length, right? So from here dl1 we can write as E1 L1, right? So dl1 equals to, so we know that E1 from Young's modulus, that is P L1 upon A1 E1, right? So from Young's modulus we know that E1 equals to P upon A1 E1. So just I substitute the value of E here. So we got change in length equals to P multiplied by L1 upon A multiplied by Young's modulus E, right? So if you have doubt, I will write here. So E1 is nothing but P upon A1 E from the previous step. Okay. So now similarly we can find out the stress in section 2, that will be 2 here, change in length in section 2 upon actual length of section 2, right? Now the epsilon 2 will be change in length of section 2 upon original length, that is L2. So here I can just change the number 2 here, 2, equals to epsilon 2 and L2, right? Wherever I wrote 1, now it will be 2, right? And area will be 2, and epsilon 2 is nothing but area P upon A2E, right? Similarly for section 3 for section 3 it will be dl3 equals to P multiplied by L3 upon A3 Young's modulus, A3 multiplied by E, right? So now I can write from this, I've got change in length in section 1, change in length for section 2 and section 3. Now I can find out the total change in length of the bar, right? Total change in length of the bar. So how much it is changed when you apply a axial tensile load for various cross-sectional area. It is not uniform, right? It is not symmetric. So let me write here, therefore the total change in length of the bar, let's say dl equals to dl1 plus d small dl2 plus dl3, right? So before steps we know that what is dl1, dl2 and dl3. Please substitute here so that you can get the total change in length of the bar. So here PL1 upon A1E plus, can you say it? Yes, you are exactly right. PL2 upon A2E plus PL3 upon A3E, right? As simple as that, right? So now from this I can take common that P upon E is common, that will be equals to P upon E. I'm taking common, that is L1 upon A1 plus L2 upon A2 plus L3 upon A3, right? So when Young's modulus of different cross section, right, the Young's modulus, when the Young's modulus of different cross section is same, if the Young's modulus of different cross section is different, then the total change in length is given as, right, given as here. I will write here. Okay, when the Young's modulus of different cross section is same, or if the different cross section having different Young's modulus, then what will be the total change in length? That is dl equals to P is common, right? Then it will be the I'm mentioning the Young's modulus will be changed, right? So that will be L1 upon E1 A1 plus L2 upon E2 A2, right, plus L3 upon E3 A3. So this will be the Young's modulus varying for each cross section. If it is same, you can take P upon E, right? If Young's modulus is different for each cross section, that is E1, E2, E3 will varies. So we can only take P as a common, that is the load, and then you can write E1, A1, E2, A2 and E3, A3, right? So that is for today's class. In this next class, we are going to see a problem on bars of varying cross section, right? So we'll see in next class that problem on bar with different cross section.